In this video, I'm going to introduce two more functions, and these are very important functions that operate on lists. They're map and filter, both of which we've already seen briefly. But we're going to re-implement them ourselves now. So I'm actually going to start by hiding map and filter from the Prelude as well, so that we can implement them ourselves. Okay. So actually, before I reload here, while I still have the Prelude version available in GHCI, let's briefly recap what we're aiming for. So the map function is actually taking a function as its first argument, and a function that can go from A to B. So it can potentially change the type, but we can choose what types to use for A and B both, so they can also keep the type, right? And then we need a list of elements that are compatible with the source type of the function, and we get a list out of elements that are compatible with the target type of the function. So as a simple example, to increment every element in a list, I could be writing map lambda x, x plus 1, and then use a list, such as 1, 2, 3, 4, 5. Okay. And perhaps in order to show you something that changes the type, I could apply map length. So length being the function that we have just been defining that computes the length of a list. If I call map length, then the type of map length is that it expects a list of lists. In this case, the element type of the inner lists is irrelevant because we're applying length to them, and then it computes the length of the inner list. So we turn a list of lists into a list of integers. Okay, so map length, and I can use a list of strings because strings are lists, right? Something like this. And we see that it computes the length of all the strings. So that is map. And let's have a look at filter as well to start with. So filter takes a test as an argument, a test that says yes or no for a value of a particular kind. And such a test is best represented as a function. We are in a functional language. Functions are easy. So we just take a function that goes from A to bool as the first argument. And again, we take a list as the second argument, a list that is compatible with this function, right, with the source type of this function. And then we return another list of the same element type, but this list is potentially shorter, so it only retains the elements that pass the test that we have been giving. So one example that we had seen before was this odd or even R function. So we can do something like map even of 1, 2, 3, 4, 5. That would give us back a list of, that is map, sorry. That would give us back a list of booleans in this case. But we want to do filter even, so that will just keep the elements for which even returns true, so it'll keep 2 and 4 in the list. Okay. Another option is to a degenerate option is to use filter with a test that always returns true. That would just give back the entire list, right? Similarly, if we use a test that always returns false, we would get back the empty list. But we can also do something like we want, for example, x to be greater than 3, and we want x to be less than 8, and then we can take a slightly larger list. So, for example, use this range notation that we've seen before of all the numbers from 1 to 100. Of course, this is not an efficient way of generating the numbers between 3 and 7, but it is possible to do it this way to obtain this result. Or we could check for palindromes, for example, like words that read the same from the left and the right. We could do something like we want to check whether the reverse of x, assuming that x is a string or a list, is the same as x, and then apply this to a list of lists. So we could do foo bar, and then something like right, and then we get the ones that are palindromes, we get them retained. Okay, so these are the two functions that we're going to try to re-implement, map and filter. So let's try to do this in our systematic way again. So we start with the type signature for map, which we already now know. All right, and then we introduce function names for the function arguments already, and start like this again. Now we have two function arguments, so I'm calling the function f, hinting at the fact that it is a function, right? And I'm calling the list access again. Now that we have two arguments, of course, we could ask ourselves, if we are going to use pattern matching, then what are we pattern matching on? Now, functions are first class in many ways, but they're not something you can pattern match on. You cannot analyze a function by looking at which constructor it has been built with. In principle, the lambda terms are sort of the constructor for functions, but they behave slightly special, and you cannot match on a lambda here. So in a function, the only choice you have is to basically pick it up via a variable pattern, give it a name, and then you can apply it on the right-hand side. So that's the big thing you can do with functions. You can apply them, and we will do that, but not yet. Okay, so pattern matching on the function is out, but we have the list, and we can do our normal systematic pattern matching on the list structure as usual. So I can split this again into two cases, one for the empty list and one for the non-empty list, and then I end up with this. Now I have lots of warnings again about names that I have introduced but not yet used, but these are irrelevant. So more interesting are the wholes. So at this point I have to create a list of type B, and I started with an empty list, and property of map is that it always keeps the shape of what goes in intact. So if you put in a list with a certain number of elements, we get a list with the same number of elements out, because the function is supposed to be applied to each of the elements. So if we start with n inputs, we get n results in the end. So here we have 0 inputs, so we also should be getting 0 outputs. So the right result here is the empty list. Okay, and similarly, if we start with the cons, right, then we know there is at least one element in the input list. Then we also produce a cons on the output. So there is also at least one output. And we keep in mind, that's the general thing about systematically defining functions on lists, that we probably want to make a recursive call of map on the tail of the list. And indeed, the rest of the list that we're going to produce is supposed to be produced by a recursive call of mapf to xs. So now we only have to figure out what's the first element of this list in this case, and that's exactly going to be f applied to x, right? Because we want to, in particular, if we want to apply f to every element in the list, we in particular want to apply it to the first element of the list. So we are going to get f of x here. Right. By the way, if I forget the f application and just write x, then my program is no longer type correct, because my type signature says, right, that the resulting list must be of type B, and we're getting into trouble, and we get some type errors that say B could not be matched with A. So we have to apply f to x to even make it type correct. Now, there is one warning remaining about the f not being used in the first case, but that is actually fine. So I'm going to replace this with an underscore again. And because if there are no elements, then we don't need to apply our function. So that is perfectly okay. Then I reload, and then now I'm in my module, right? I mean, and I can try whether my map function works like the original map function did, and whether it behaves sensibly, right? It's perhaps even good to like introduce some kind of mistake to really be sure we're testing the right map function, right? So now I'm producing. This is still type correct. I'm producing 2 copies of every mapped element. So with this definition, I'm getting this funny list here where I have 2 occurrences of every number. So that seems to be fine. So I'm actually checking the function that we have implemented and not the Prelude function. Okay. Let's move on to filter. So the type signature of filter was this, right? We take a test that is from A to bool and a list of A's, and the list of the return type is a list of A's again. So we have 2 arguments. So here I'm going to call I could call the function f again, but I'm going to call it p for predicate, right? So and I'm going to give a name to the list, which is xs again, and I'm again starting like this. But it's again the same principle. There is no hope of gaining anything from pattern matching on a function, but we can make the problem simpler by pattern matching on the list. So let's split on the list, and then we get these 2 cases. And then again, we start with the case for the empty list. We have to produce a list of A's here. Now, filter does not always produce something of the same shape, but it always produces a shorter list. I mean, a list that is no longer than the original list, right? So it does not invent any elements. If anything, it removes elements from the list. So if the list we start with is already empty, then again, the result list is also going to be empty. Okay. Now, in the case of the cons, we have to look at p of x. And p of x is a Boolean. And depending on the outcome of the Boolean, we have to do multiple different things, right? So depending on whether p of x is true or false, we have to do multiple different things. And there are various different ways of doing this, but they are all things that we have not yet been discussing. So that is something actually new that we are introducing at this point. So I'm going to go through 3 different variants briefly. One is mostly for later, and the other 2 are actually proper idiomatic solutions in this case. So one solution is to take the viewpoint that what we really want to do is to pattern match from the result of p of x. Boolean is just another data type, a data type that has 2 constructors, as we have seen before. You can use ibool here. Look at the definition of Booleans have false and true as constructors. And I can say, well, I could want to do a pattern match on p of x, and I have a case for true and have a case for false. And that is actually something that is possible. I could even define a new helper function, call it with p of x as an argument, and then perform a pattern match on there. But there is another construct in Haskell, in the expression language, that we can use to perform a local pattern match on an intermediate result, and that is called case. So I can say case px of, and then I can say I have 2 cases, one for false and one for true. Okay. Now, there are a couple of things to note here. So one is we now have a definition, an equation that spans multiple lines. if a definition spans multiple lines, then layout becomes important. You have to indent the subsequent lines of the equation compared to the original line, whereas the original equations all have to start at the same column, right? And again, if you have a case, then all the different alternatives in the case have to be indented, and they have to start at the same column. And then there is a pitfall here, that namely that there's a right arrow being used syntactically to delimit the left-hand side where the pattern is in the case, and the right-hand side where the result is in the case. So this is a right arrow and not an equals. Otherwise, we put an expression, in this case p of x, between case and off. This expression is of type Boolean. P applied to x is a Boolean, and we just match on the result of it. So these are patterns for Boolean. If p of x is false, right, so if the test fails, then we do not include the element in the result list, but we still make a recursive call, so we call filter p on xs. If p of x is true, then we do keep x in the result list, so we produce x cons, and we also make a recursive call. So again, right, this principle of making a recursive call is maintained. And it looks a little bit like we're doing two recursive calls here, but we are really only making one, because only one of these two branches is ever going to be executed, right? P of x is either false or true, so but not both. So this is fine. We still have a warning for p again, and again, we are not actually going to use the test in the situation that the list is empty. So, so we can replace this with an underscore. So this is a perfectly fine definition of filter, and it actually works as expected, right? Or let's try to get back to our palindrome example. It does work, okay? Now, Booleans are also slightly special in the language. Lists have a lot of extra support. Booleans have a little bit of extra support. So while this case expression is perfectly general and can be used to pattern match on intermediate results of any type, for Booleans we actually have better options in the language that are basically syntactic sugar for a case statement like this. And in particular, we have if then else, right? There is an if then else expression that you can see as just an abbreviation of such a case expression, only that it would have been better if I had flipped the two cases, which I'll just do as a starting point. So rather than writing a case, I can write if p of x, and then rather than the two branch, xcons filter pxs, else filter pxs. So it basically means the same thing as the case, right? So if the condition here is true, then the result of the if then else expression is the part after the then. If the condition is false, then the result of the if then else is the part after the else. It's an expression, and there's always a result, p of x, or the condition that we're putting there is either true or false. The then or the else branch is taken. So that means in particular that you cannot just omit one of the two branches. You cannot omit the then branch or the else branch, right? That doesn't make sense in this case. In other languages, if then else is often a statement. If you're familiar with this question mark colon operator from, say, Java or C, then that is more what's corresponding to an if then else expression. So that is one other option, and we can convince ourselves that if I reload this, that it still behaves in the same way as expected, right? There is a third option, and that is guards. Guards are yet another option of like writing Boolean conditions, but they become part of the declaration, part of the binding itself. So if then else is just an expression, and it can appear anywhere where an expression can appear, even like deeply nested as a function argument to something else, right? But guards can only appear at the top level of a binding. So rather than putting an equals symbol here, what we could do is we could, typically one starts a new line which is indented, put a vertical bar, and then put a Boolean condition such as p of x here, and then say what happens if p of x evaluates to true. Well, then we give back x cons filter pxs. And then we can put more Boolean conditions here, and actually arbitrarily many, and they would all be checked in order. And the first one that evaluates to true is being taken. So if we want to say something like else, then what people are typically doing is they give a Boolean condition otherwise. And here we write just the recursive call. Now, what's otherwise? Otherwise is really just a constant that is predefined in the prelude, which is of type Boolean, so it can be used as a Boolean condition. And it is just another name for the constant true. So we could alternatively have been written true here. It's a condition that just always succeeds. So then we like have the last case, we have one that always matches. It's more idiomatic to use otherwise here, but it means the same thing, right? So that's the idea. So you can use a case expression, you can use if then else, you can use guards. Now, a case expression is the most general approach, but I would say in the special case of Booleans, the other two options are better. They are more idiomatic, right? If then else or guards is mostly a matter of taste. I think if then else is slightly more clunky than guards, but it is also more flexible, because if then else, as I said, can be appearing anywhere where an expression can appear. So I would probably typically use guards if it's a condition that is arising at the top level, because it looks slightly nicer, I think. But it's a relatively minor stylistic difference, and it's mostly a matter of personal taste. I think both are used actively. And yeah, that concludes both map and filter as functions. As we've seen, the standard design pattern on lists is appearing again and again, and that's also why it is so important. Really, most of the functions are just following this.